This question, in my opinion, takes a bit of time to get your head around. We're trying to basically find a set of numbers from 1 to some maximum amount. I mean, it's obviously linked to this 2k bit, but some maximum amount where we can put the numbers into two different sets of equal size, and then we're not going to have any of the numbers sharing more than two distinct prime factors. So, 3 times 5 times 7 and 3 times 5 squared times 7. That would be a problem. But what is the largest value of k for which we can make this group of 1 to 2k? 1 to 2k numbers, and it's the numbers 1 to 2k. Well, I think the starting point is to just write down some numbers in power form. Then they're in their prime factorization. So 1, obviously not prime, but 1, 2, 3, and then we can write down 4, 5, 6, 7, 8, so I got up to 10. Okay, so all of these numbers actually, if I was to say like k equals 5 and 2k is equal to 10, then I've got to try and split these now into two equal size groups such that none of them share more than two distinct prime factors. Actually, that is very simple because they have at most two distinct prime factors themselves, so there's no way that they could share more. And so actually, in this case, we could just do 1, 2, 3, 4, 5. Actually, you could do it any way you want as long as you've got 5 in each group, and then 6, 7, 8, 9, and 10. So that's okay. I know that I know that k is going to be greater or equal to 5. I mean, just as a little kind of starting point. I mean, we could now try some larger numbers and repeat this sort of process, but really now we want to get into the main bit of the question, which is about, share no more than two distinct prime factors. So let's find the first number that actually has three distinct prime factors. So lowest number. But when I did this question, this does not immediately occur to me. I think it's a good idea in these challenges to just see what works, see if you can make it work for the first few, get you kind of a feel for what the problem is actually saying. So lowest number with three distinct prime factors is in fact going to be the product of the three smallest primes, 2 times 3 times 5, so 30. Now, it's going to be possible for 2k to equal 30, and hence k equals 15, because I could just, again, split it into my groups, my two different groups, and I could put 30 in one of them, and all the rest would have at most two prime factors. So that would be okay. So the question then is, how is 30 going to sort of get into trouble with other numbers? And we can look at numbers that also have 2, 3, and 5 um, as prime factors. So 60 would be one. So if I square the two, 2 squared times 3 times 5 equals 60. Also has these prime factors. So you see, it's not that long until we start getting into difficulties. Thing is, at the moment, we could put the 60 in the other group. Yeah, because then they wouldn't, because if we put them in the same group, that is when things go wrong, because then we would have in the same group, they would share three or more than two distinct prime factors. So that is not going to be okay. But 60 is still okay because we can put it in the left-hand group. So it seems like I haven't kind of proven it, but it seems that 2k equals 60 is okay. So put 30 and 60 in opposite groups. Now, the thing is, we have to remember that there are other numbers up to this like probably maybe between 30 and 60 that have three distinct prime factors. 2 times 3 times 7 would be the next one with three distinct prime factors, but prime factors different, um, which gives 42. But actually, they're not shared with 30 or 60, so it's not really an issue. Okay, so the next one would then be the next multiple of 30, actually. So 2, sorry, not 2, so 2 times 3 squared times 5. I'm now tripling the 30, and that gives me 90. Okay, so now there's a problem because we get our two groups, and we can put 30 in this one and 60 in this one, but where does 90 go? And the question is, it can't go anywhere. We need that 2k is less than 90. We can't go from 1 to 90 because at that point, I've got these numbers that have three shared prime factors, only two groups, so I can't put the 90 in, or I can't put the 30 in if I put the 90 in. So 2k must be less than 90, and therefore k is less than 45. Hey, that's pretty good, okay? Because we've gone from like not knowing whether, you know, knowing where the largest possible value is at all, is there a largest possible value, to finding that yes, there is a limit, and it's got to be less than 45, okay? And hopefully I've convinced you that that is the case. So really, we're just left to then check in if what the largest value of k is, like maybe it's 44. So try k equals 44. We know that 45 doesn't work. We've explained why, but surely 44 works because I don't then have this, this kind of collective three where they shared factors. So then 2k would equal 88. Let's try putting it into groups. So I've just got to make sure I split up the 30 and the 60. So I don't want to write all of these out. I mean, that is, to be fair, that is something in this for the sake of the challenge. It feels like that would at least be convincing. Um, so if in doubt, write them all out, I guess. But I'm not going to do that. So I'm going to write them all out up to, it's going to be 44. So 2 squared times 11. And then it's going to be 45, which is 3 squared times 5. 46, which is 2 times 23. All the way up to 88, which is 2 cubed times 11. So this one contains 30, and this bottom one contains 60. So I highlighted that in my answer, and then I said all the other numbers have two or fewer prime factors, or three prime factors that are not all 2, 3, and 5. E.g. the 42 from before, okay? I can't just say they have two or fewer prime factors because as I showed you, 42, it will be in there. It's just that it's got 7, so it doesn't share it. Therefore, this works. K equals 44. What did the question say? Is the largest possible value. Now, yeah, it's probably not enough, to be fair. if I wrote them all out, I feel like it would be enough because it would be like quite clear. But have I really made a convincing argument that definitely there's no other, ones that share it? So I'm not sure about that. So I'm going to kind of revert to the answer at this point. So they did a very similar thing. They split it into 1 to 44 and then 45 to 88. And then they argued we need to show that using this way of splitting the numbers, there are not two numbers x and y which share three prime factors or in the same group. So yeah, x is less because we're putting x in the smaller group. It's going to be less than y, and that's going to be less than or equal to 88. So let's say they share three prime factors. Then we can argue that x and y will be multiples of PQR, these prime factors. And then as 3 times PQR is greater or equal to these are our lowest ones. Okay, because remember, we've already found that 90 is not in the group. Um, so because this is greater than equal to 90, then which is greater than 88, we have that x has to equal PQR and y has to equal 2 PQR. But then we see that basically it's not going to work out. I don't know. This is quite technical. I've got to be honest. So it is. I agree. It's better than my solution, but it's pretty. It's very technical and obviously like very rigorous, but quite difficult to see to get that. I think so. Have a look at this and get your head around it. Um, my way, a little bit sloppier, but I get the main idea across. And kind of think if you write them all out, then that would also be good. But obviously, for more numbers, that method would fail. So that is my best attempt at this question. I actually found this question maybe the hardest question on the paper, especially to kind of understand what was going on and then explain. But the very last question, number 6, is also got that challenging aspect to explain as well. Okay, well done for watching this, and I hope it makes a bit more sense. Thanks.